Good question here. I'm impressed that Larry can kick a football vertically upwards. Most people don't actually manage a complete vertical kick, but that's okay. We've got a speed, initial speed of u meters per second, and it's a 0.9 meters above the ground. Okay, and it reaches a height of 10.9 meters above the ground. So the distance traveled is actually exactly 10 meters. So what we need to do is we need a diagram. So we've got the ground, we've got a 0.9 meter, and we have an upward velocity of u. We've got, if I can get this to draw, going up to 10.9 meters, so therefore this bit here is 10 meters. And if it's at its highest point, and that's the key piece of information, greatest height, the implication is that it's run out of speed, its velocity is 0. And the other thing you need to do is you need to show that gravity, and I'm going to choose to put gravity acting as a negative force because my initial sense is upwards. Some people like to put a plus in there, and of course you can have the whole thing going backwards, but it doesn't really make any difference. And I'm going to use a constant acceleration equation. So fairly happily, I'm going to use the one that connects final velocity, which I know is 0, u squared plus 2as. Okay, and this is one of the cases where s, distance, being vertical, doesn't fit with physicists' x, because of course for a mathematician that would be y, but we're not going to argue that. S for spatium. So what I've got is 0 squared is equal to u squared plus 2 times minus g times 10. Now, of course, g for a mathematician is 9.8 meters per second squared. Okay, it's an acceleration, that's why I've got a double arrow in there. So essentially what I've got here is that 0 is equal to u squared minus 196, which gives me that u squared is equal to 196, hence u is equal to plus or minus 14, but in this particular case u is equal to 14 because it is going in my positive direction. Technically, if I'd got it all acting the opposite way, my u would have been considered to be minus 14 meters per second, but that's not really that relevant in this particular case. Now I need to find the time between the ball being kicked and the ball hitting the ground. And I've got to give my answer correct to 1 decimal place. And if it says 1 decimal place, it wants 1 decimal place. If you're too accurate, then it will be a bit of a problem. Again, I need my diagram. This is its initial point. I've again got gravity acting down because I always consider going up to be my positive direction, so I'm going to put my positive direction in, and what it's going to do is it's going to go up and it's going to come down, and I want to know the time at which it reaches that ground there. Now that, given that the original height that it was kicked at was 0.9 meters, that means that this is minus 0.9 meters below its starting point, minus 0.9. So I want something that connects. My u is 14 because that's the velocity that it was given upwards. Gravity, time, and distance. So the obvious one in that particular case, because we're in constant acceleration questions, is s equals ut plus 1/2 at squared. And this is very, very common because it gives us two answers, one of which you're going to have to get rid of. Sometimes your brain doesn't work. So we know that s is minus 0.9. We know that u is 14. We don't know t, that's what we've got to find. And we do know that if g is 9.8, half of that is going to be 4.9. So I've now formed a quadratic. If I want to solve that quadratic, it's got to be equal to 0. Now, I personally always like my square term to be positive. So therefore, I'm going to treat my quadratic as this. But I've formed the quadratic, which means I'm actually doing most of the marks already. Now I need to solve it. Now there is no way in this world that you are going to solve 4.9t squared minus 14t minus 0.9 equals 0 by factorizing. You have got to use the formula, and it is not a bad idea under exam conditions that you actually show that you know how to plug the thing into the correct formula. You don't have to quote the formula, but if you do use a formula, make sure you use it correctly. So 14 squared minus 4 times 4.9 times minus 0.9 all divided by 2 times 4.9, which of course is 9.8 again. Now at this point, we know that your calculator does this particular piece of work for you. I'm not going to tell you how to go through that. You should know it. Your calculator will return to you if you persuade it, and I would personally like to see both answers. You need to do that to show that it's going on. And you need to be explicitly considering the positive answer, because the square root of 109 is bigger than 10, so 10 minus something that's slightly bigger than it divided by 7 gives you something quite small, but it is negative. That's before you started. So it is 10 plus the root of 109 over 7. Press your trusty SD button, third to decimal, and you get a dobbing great number, 2.9200437787. Question asked for 1 decimal place, 2.9 second to 1 decimal place. Now, it doesn't often ask for those sort of degree of accuracy, but use it every time. Now, again, I've got writing going on here, but I'm not going to do any. When I was drawing my diagram, I drew the object as a particle, and I assumed that the gravity was always the same. So I am assuming it's a constant acceleration question. If you were listening carefully to what I said, I actually said that right at the start, assuming constant acceleration. So the assumptions I've made is that I could actually model it as a particle. In other words, its dimensions don't make any difference. and that gravity is constant, or that gravity is constant in this particular case. Now, in my original diagram, we have, in this particular case, we've got a lighter ball. Now, Laura is obviously a very good person at kicking the ball, but she's not very good at thinking things out, because these accelerations don't rely on anything to do with mass. So, according to this theoretical model, there's nowhere in this particular setup for the mass to come into play. So the fact that it's lighter means that if she kicks it at 14 meters per second, it will stop at 10.9 meters again, regardless of where she's doing it.
Just a little bit of bonus material, as it were, for this question. And looking back at part B, so this is when the ball had started 0.9 meters off the ground and was projected upwards with a velocity of 14. We had acceleration downwards of g. Up was our positive direction, and having solved the s equals ut plus half at squared, we ended up with t equals 10 plus or minus root 109 over 7. And since obviously the time had to be positive, then the conclusion in the question after rounding was that the time was 2.9 seconds. But it isn't necessary to talk about this in the question, if it were in an exam. But the fact is that this formula gives us another answer, which I'll do to 2 sig figs. Minus 0.063, so hardly any time at all. And I wonder if you've discussed in lessons or thought about this yourself, if a formula gives an answer, does it mean something? Well, it does, as it happens. And what it tells us in this case is if we were to be able to go back in time, then for the ball to arrive 0.9 meters above the ground with a velocity of 14, it would have been sent off from the floor, and it would have taken 0.063 seconds to get from the floor to the starting point in the question. So to investigate that a little further, let's imagine the ball starting at the ground. Then what would we know about it? Well, if we write our SUVAT out, which is how I like to do these questions, then it would be travelling 0.9 meters upwards. The time it would take to get to that 0.9 meters would have been 0.063. Its final velocity would have been 14, and these are all positive because we're still taking up as our positive direction, and A would be minus 9.8 again. Now, one of the SUVAT equations which often isn't used and sometimes isn't taught is that as well as s equals ut plus a half at squared, we have s equals vt minus a half at squared. And so we can check that these figures will work in there, just to check that this interpretation makes sense. So putting the numbers in there, we get 14 times 0.063 minus a half times minus 9.8 times 0.063 squared, which gives us 0.90, two significant figures. And so it does make sense. So what the second root in this equation gives us is a look back in time. So that is what the other root denotes. It makes sense in the system, given that we know the ball was travelling at 14 metres per second when it was 0.9 metres above the ground. The fact that it was a kick that made that happen is irrelevant to the SUVAT formulae.